We are starting off chapter 8 with some notes. Won't go right into the homework problems. We'll start with the notes. Okay, looking at an equation, something we are familiar with is sodium, metal, solid. It's pretty reactive stuff. Chlorine gas, also pretty reactive stuff. Both kind of in a bad way. You wouldn't want to deal with them, either one of them directly. And we know when these guys react. I'm going to remove the 1/2 thing. Well, why not? I'll leave it there. And when these guys react, you get sodium chloride, solid, which we're not too terribly concerned about. It's around, you put it on your food, it's certainly safe stuff. And this reaction definitely takes place. But there's a lot of steps along the way in this process that don't necessarily make sense. And it's this last step here, which we'll come to in a few minutes, that actually kind of like, oh, now I see. So there's some things we kind of take for granted and we just think they work, but they don't work well. And it's only because there's this last step involved that really is very, very favorable. So let's take a look. First thing we're going to just kind of fool around with here is we'll say we have some sodium solid, and we're going to take that and we are going to put it in the gaseous form. That may sound weird, but yeah, it's necessary and we can do that. Now, as far as its energy, going back to chapter 5 stuff, it has an enthalpy value. In other words, we have to invest, that's a positive, amount of energy of 108 kilojoules to make this go. So we have to invest energy to heat it up, and that makes sense. Now, if we move on over to chlorine, chlorine is diatomic. It's one of those Hofbrinkels. It's normally a gas at room temperature, so we don't have to do anything to that directly. But if we want to break this bond and form just chlorine atoms, so we're going to break the bond that connects these diatomic atoms. And I really just want to focus on one, which is why I put the 1/2 in there. That total amount of energy for one of them to break that bond would be 122 kilojoules. So that's the energy we have to invest for this as well. Now that we have sodium gas, going back to step 1, if I want to turn it into an ion, remove one of those electrons, which is what we talked about before. Say, oh, sodium wants to lose electrons. No, it doesn't want to lose electrons. You have to pry it away because of the positive-negative attraction these guys have for each other. It requires a lot of input energy to remove that electron. So you can see it's not favorable. You have to put energy in to take that electron away. And then the last one we'll put up here as far as a beginning stage, we finally get one that sort of works. Electron's negative, the nucleus is positive of chlorine. There's an attraction. So when you turn chlorine atoms into chlorine ions, that is actually favorable. Negative 349. Now, I haven't done any math behind the scenes, but adding all these guys up, it looks like it's a net positive, which means not favorable. So it's an endothermic process. You have to put energy in to make this work. It's this last step here in which you have sodium ions and chlorine ions, both in the gaseous. No, this is going to be negative. These guys coming together as ions and forming ultimately a solid that has a final, in itself, a very exothermic reaction that allows this overall reaction to be negative and favorable. So yeah, when you take sodium metal and you introduce it to chlorine gas, it works. And it's this last step in which you are looking at the lattice energy that is the key to making this work. It's only because of that that this overall reaction takes place. So let's talk about lattice energy. Lattice energy is what is required to separate 1 mole of solid ionic compounds into its gaseous ions. There's a lot going on here. First, notice how we wrote this definition out. It was almost kind of the reverse of what we actually showed in this process. We were talking about this as far as forming the ionic compound. This definition is written in the opposite direction, separating the solid into its gaseous ions. That's the way it would work. The amount of energy is still exactly the same. It's just which direction you're going. So I would have to invest this amount of energy to turn it into its ions. It's the energy released when it forms a solid. Now, this is something very important to keep an eye on and remember, that we're specifically talking about ionic compounds. Do not try to have this conversation if you want to talk about molecular compounds. Remember, molecular compounds are held together, which we haven't talked about a lot yet at all, really. Molecular compounds are non-metals. Carbon, oxygen, nitrogen, phosphorus, hydrogen, those kind of things. Ionic compounds, metal, non-metal, metal, non-metal. So we're talking about ionic energy, or excuse me, lattice energy, when you're talking about ionic compounds. So that's where this conversation comes into play. Okay, now as long as we're talking about this, let's keep digging in a little bit more. We mentioned this formula a while ago, and it's coming back around. It was Coulomb's law. So remember, these are the charges of the ions. K is a constant. We don't need to worry about this. This is the electrostatic potential energy of these ions coming together. This is the distance between them based on their averages, their radius. So let's take a look at now, as far as the primary factor, you have both of these factors. So the smaller the radius, the more potential energy, the lattice energy will go up. And as the charges go up, +1, +2 kind of thing, -1, -2, that'll also make this value go up, numerator, denominator. The charges is the predominant factor. That is, of course, going to go up at a higher magnitude than the radius will. So let's do a little problem question here. Arrange sodium fluoride, cesium iodide, and calcium oxide in increasing lattice energy. So you're going to arrange these 3 ionic solids, compounds, in order of increasing lattice energy. So smallest energy first. One of the things I would grab on first is the charges. +1, -1, +1, -1, +2, -2. So we said the charge is the predominant factor. So these 2 factors, +2, -2, that is going to be the largest one. So we got that taken care of. So now we'll do sodium and cesium and fluorine and iodine. And maybe I don't know this right away, so I'll bring on over our periodic table. Looking at sodium and cesium, cesium's bigger. So as the radius gets bigger, that would tend to favor this being smaller in the denominator. And then if we have the other 2 are fluorine and iodine, fluorine, iodine, iodine's bigger, so that also should make it smaller. So it looks like the one that's going to have the lowest lattice energy would be cesium. So I'll put this as far, well, I'll go ahead and put it in order. Cesium iodide will be the lowest, followed by sodium fluoride, and the largest lattice energy would be calcium oxide. Okay, end of lecture 1.